In this lesson, we're going to be graphing quadratic functions using the critical features that we learned about in the last two lessons. This is a great lesson because it is a compilation of the last two lessons. It's going to be good practice not only with graphing, but also finding those critical features of the quadratics like the axis of symmetry and the vertex. We're going to use those to make our graphs. So let's start by graphing a simple quadratic like y equals x squared plus 2x minus 3. Normally we jump right in and we make our xy chart. This time we're going to give a little more thought to it first. We're going to start by finding some of the critical features, like the axis of symmetry. Here's our formula for the axis of symmetry, x equals negative b over 2a. And you all know where the a, b, and c values come from. So we end up with a negative 2 over 2, which is a negative 1. So I'll plot that on my graph. There's my axis of symmetry. Now I know my parabola is going to be symmetrical with respect to this line, this vertical line. We can use this to now find the vertex. We already know the x-coordinate of the vertex is going to be negative 1 because the vertex must lie on the axis of symmetry. So to find the y-coordinate of the vertex, I will plug in the negative 1 into the function, and I'll end up getting y is equal to negative 4. I'll plot that on the graph. What else could I find easily? One thing I could find very easily, besides the axis symmetry and the vertex, is the y-intercept. The y-intercept is the c value, which is negative 3. So I'll plot that on the graph. It's right here. I could use symmetry to get a point on the other side, but that still would only be 3 points, not really good enough to make a parabola. So I'm going to go for some other x values. Like I'm very interested to know what is y when x is 1 or 2. So I'm going to make a small xy chart, not a real big one this time, just a small one, and I'm going to plug in the values 1, 2, and 3 so I can get an idea what this function looks like at those values. So when x is 1, we end up getting 0. So that's your x-intercept. That's one of your x-intercepts. When x is 2 and I plug that in, I end up getting 5, which is way up here. And I can probably see that 3 is going to be way up there, but I'll go ahead and figure it out. It's 12. Yeah, that's beyond my graph, so I'm not going to worry about that point. But now I can use symmetry to get these points on the other side. And I have now, looks like 7 points with not too much work. And I found most of these points algebraically, and I know how to do this now in a different way. I am finding the critical points, and this is reducing the size of my xy chart down to just 2 or 3 points. Let's do this one. We'll start by finding the axis of symmetry. We get x equals 1. I'll plot that on the graph. And now let's find the vertex. We plug 1 into the function. We know the x-coordinate is 1. Now what would the y-coordinate be? The y-coordinate is going to be 9. So my vertex is at 1, 9, way up here. Now what else can I find easily? We know it opens down because of the negative quadratic term. We can also find the y-intercept pretty easily. The y-intercept's 8. That's right here. And I can also do other points. I'm interested in, let's say, negative 3, negative 2, negative 1 would be good to know. When I plug in negative 3, I end up getting negative 7, which is way down here. When I plug in negative 2, I get 0. When I plug in negative 1, I get 5. And now we can use symmetry to get points on the other side. And there's our parabola. Nice looking parabola. So let's take a look at a word problem here. We have a golf ball following a parabolic curve. The curve is represented by y equals negative x squared plus 8x, and we need to find the maximum height, which would be the y-coordinate of the vertex. So I'll start by making a graph. This is going to be a first quadrant graph since height and time are both going to be positive. You can't have negative height or negative time. Let's start by finding the axis of symmetry for this equation. We get negative 8 over 2 times negative 1. That's going to be x equals 4. So if I scale my graph by ones like this, I can put a vertical line right here at x equals 4, which represents 4 seconds. Now, since that's the axis of symmetry, which also represents the x-coordinate of the vertex, I can easily find my vertex by plugging in 4 into the equation. So I end up getting 16. So 416 is where my vertex is. In order to hit 16 on the y-axis, I'll scale this by ones. And here's my vertex at 416. That means after 4 seconds, it reaches a maximum height of 16 units. So what would the y-intercept be? Well, we know the y-intercept is 0. So we know that the golf ball started with an initial height of 0. In other words, it was hit from the ground. It had no initial height. And because of symmetry, I also now know where the ball is going to hit the ground, or when it's going to hit the ground. It's going to hit the ground after 8 seconds. I can tell that immediately because I'm 4 units away from the axis here. That'll put me 4 units away on the other side, so I know after 8 seconds it's going to hit again. But this wanted to know the maximum height reached by the ball, which I already know is 16. I could do a few more points just to fill in the graph, which I'll do. And again, I could use symmetry to figure out most of these points, but that's what your parabola looks like. The maximum height reached by the ball was 16 units. And the time that the ball was in the air was 8 seconds, even though it didn't ask that question.